in terms of the computer implementation, the way we do the computer program is like this. First, we let the index k equal to 0. That corresponding to the so-called the computation of vector f4 of the index k. And please remember, the index k could be anywhere from 0, 1, 2, 3, 4, 5, all the way to capital N minus 1, which is equal to 15 up in this case. So the first thing we say is k equal to 0. Well, in the binary form, 0 can be expressed as 0, 0, 0, 0. So if you already compute the F4 at the location 0, 0, 0, 0, when you do the so-called reversion of the bit order, 0, 0, 0, 0, when you reverse it, it still becomes 0, 0, 0, 0. So the original value k equal to 0, and when you reverse it, the value you call it I is also equal to 0, and because k is the original value, the value after you reverse the bit is I is also the same. Therefore, when you go to this block of the if check, in this case I is not greater than k, because in this case I and k, they are both the same, equal to 0. It is not greater than k, and basically what it means is we skip this part because that if statement is not satisfied. And what it means is f4 of 0, f4 at location 0 now also remain f4 at location 0. There's no swapping. The next thing we do, we let the do loop index k equal to 1. Again, in binary form using r equal to 4 bit, the value 1 can be expressed as 0, 0, 0, 1. So the value of k is equal to 1, which is the same thing like 0, 0, 0, 1. When you reverse the order, then 0, 0, 0, 1 will become 1, 0, 0, 0 when you reverse the order. In other words, instead of going this way, you reverse it, it's going this way, then it will become 1, 0, 0, 0. Well, this number 1, 0, 0, 0 in binary form is having the same meaning like the value is equal to 8. And the reason is, I told you before, this value 0 here, you have to multiply with 2 to the power 0. This value 0 in here, you have to multiply with 2 to the power 1. This value here, 0, you have to multiply with 2 to the power 2. And this value 1 in here, you have to multiply with 2 to the power 3. And so when you add all of those things, you get the answer is equal to 8. So what does that mean? The old location, which is k equal to 1, should be moved to the new location I, which is equal to 8. So now let's see what happened to this do loop. The same thing similar like before. If I greater than k, then do blah blah blah. Well, in this situation, I is equal to 8, k is equal to 1. So that if statement is satisfied. Because that if statement is satisfied, so you go into the next statement, which say f4 of k, that means f4 of 1. You store that value in the temporary array, temporary variable called t. And then we say f4 of k, which is meaning f4 of 1, is equal to f4 of I, which have the same meaning like f4 of 8. And then after that you say f4 of I, which is f4 of 8, is equal to t. T means the original value of f4 of 1. Okay? And if. So what it does here is this variable named t, it will store the original value of f4 of 1. And the reason is because after that, the original F41 will be destroyed and replaced by the new value, which is F4 of 8. And that's why we need to store the original value of F4 of 1 in the temporary variable name called T. So after you get out of this loop, basically what it says is F4 of 1 become F4 of 8, and F4 of 8 become F4 of 1. In other words, these two values will be swapped. Then you move on to the next index. Now you go on the do loop index k equal to 2. Again, 2 can be expressed in the binary form as 0, 0, 1, 0. So when you reverse the order of that, so you go in this opposite direction, when you reverse the order, it will become 0, 1, 0, 0. And that is exactly what I show you in here. And again, corresponding to the binary representation 0, 1, 0, 0, it means the value is equal to 4. So again, in this case, because the index I, which is equal to 4, is bigger than the index k, which is equal to 2, and what it means is we have to swap F42 become F44 and F44 become F42. We have to swap. Similarly, we just do 2 more to make sure you understand. The next time we let k, the index k equal to 3. Remember, the index k have to keep increasing 0, 1, 2, 3, 4, 5 all the way until capital N minus 1. Alright? So when the index k equal to 3, 3 can be represented in the binary form as 0, 0, 1, 1. And therefore, when we reverse the order of those bits, 0, 0, 1, 1, when you reverse it, it will become 1, 1, 0, 0. And 1, 1, 0, 0 mean the value equal to 12. So again, in this case, because the value of I, which is 12, is bigger than the value of k, which is 3, therefore we have to swap F4 3 become F4 12, and F4 12 become F4 3 at those locations. Now, the next thing we say is what happens when the next index k equal to 4? Well, when k equal to 4, 4, if you express in the binary form, it have the same meaning as 0, 1, 0, 0. However, 0, 1, 0, 0, when you reverse the order, that means you go in this opposite direction, it will become 0, 0, 1, 0. It will become 0, 0, 1, 0 when you reverse the order. And 0, 0, 1, 0, it have the value of 2. Now, in this case, because the value of I, which is equal to 2, is less than the value of k, which is equal to 4, that means we don't want to swap between the location 4 and the location 2. Well, the reason we don't want to swap it is very obvious. And the reason is because earlier we already swapped. You can see that F42 and F44 we already swapped. And that's why at this step in here, we don't want to swap again because that has already been done. So basically, what I'm trying to tell you is that if you go to make a do loop of the index k, let's say going from 0 all the way to n minus 1. And within that do loop, you just write out this kind of code. Then at the end of the process, then what happening is you can see all of these 16 numbers that you calculated in here for the vector F4, it will be moved to the new location according to the right order, like what we would expect to see in equation 7. So this basically finishing the so-called the unscrambling process for the fast Fourier transform. Okay? Now, the next step I want to do will be, let us try how do we do the computer implementation for the fast Fourier case. At this moment, I assume the number of data point capital N can always be expressed in the form of 2 raised to the power r, where r must be an integer number. That seems like there's some kind of a restriction there. However, we will remove that restriction very soon. Now, according to the couple of equations that I already developed for you earlier, at that time, I think you probably still remember we have a formula which says something like this. We have a formula which says something like the vector f at the level L corresponding to the index k will be computed based on this formula. FLK is equal to the vector vector f at the previous vector in the previous vector level, which is L minus 1, at the same location k, plus the vector f of the previous level, which is L minus 1, of the companion node of k. Well, the companion node of k is equal to k plus a distance. And I hope you remember that distance is given by n divided by 2 raised to the power L, which is the level. Okay? So that is a formula that we developed for you earlier. Now, if you look at that formula, the problem is that everything in that formula is a complex number. This one in here, that formula, we're supposed to multiply that also with a weighting factor. And that weighting factor, at that time we call it W raised to the power P. Okay? So that is the right formula at that time that we developed. Now, in that formula, everything is a complex number. FL is a complex vector, and W, P, everything is a complex number. And a lot of time, it is not convenient to write a computer program dealing with a complex number. So for that reason, what we suggest to do for computer programming is every complex number we can express as the real number plus I times the imaginary number. So for example, you can see clearly the vector FLK could be expressed as FL real K plus I FLI K. Now the advantage of doing this is that this number FLK and that number FLI, if you exclude the I in the front, both of those numbers are real number if you exclude the I in the front. Similarly, you can see on the right hand side, instead of saying the vector FL minus 1K, that number right there in the red color is the complex number. But that number right there, FL minus 1K, can be expressed in this form, which consists of FL minus 1 of R, mean the real, plus I times FL minus 1 of I. So if we express FL minus 1 according to this fashion, then again the advantage is that FL minus 1 of R is a real number, and FL minus 1 of I, capital I, is also a real number because this I in here already outside. And again, remember the definition of small I square is equal to minus 1. And the same thing is again, we can express we can express